Well, good morning. Welcome to Algebra 2. This is lesson 8.3C. That's the homework due on Friday is 8.3C. It's a worksheet paper submission. I'll be handing out before the end of class today. Also, I'm teaching 8.4A today also. That's actually Friday's lesson, but we are anticipating that, even though we're not asking people to be absent on Friday, in the event that anyone is absent on Friday, maybe they feel like, 1 week off of school, a week and a day isn't enough, and you want to take an extra day on Friday. Well, we are, I guess, in some ways enabling that by putting this video up there and teaching Friday's lesson today, so that on Friday when you get to class, we'll be able to practice, do the homework in class, play the hot dog game a little bit. That's going to be the plan for the rest of the week. So let's take a look at these practice hot dog questions for today. Number one, this is a practice hot dog question. What I'd like you to do is sketch the graph of f of x equals negative square root of x plus 6 and list the domain and the range. So sketch the graph of this function, list its domain and range. That's going to be a preliminary step for finding the inverse function and its domain and range. So practice hot dog question, give it a go. Please write your answer on your collection of hot dogs. Alrighty, well, let's start talking about this one. Some of you appear to be stuck, and it's possible that the experience of being stuck could be caused by not taking time to really document the transformations. So, by the way, the parent graph for this function is the square root of x parent graph. And based on what we see in this expression, what transformations would occur? In particular, what transformation is caused by this negative sign out front? Sophia, what would your interpretation be for this? Yeah, so essentially that negative sign is not influencing x because it's outside of the square root. So you could bring it over to the other side. It's really affecting the y-axis, the y coordinates. So you've got to ask yourself, if you take every y coordinate on this graph and make it negative, what would the effect on the graph be? Would it reflect this graph over the x-axis or over the y-axis? If you took the opposite of all the x's, it would reflect it all over y. But if you took the opposite of all the y's, it would reflect it over x. So those of you who are stuck, and there were a few of you as I was touring the room, just write, because of that negative sign, we're going to reflect over the x-axis. And then how about this plus 6? What's the subsequent transformation that will be triggered by the plus 6? Go ahead, Alana. And that's going to be left 6. So that's your hint. That's your hint for getting this graph. Take the parent graph, reflect it over the x-axis, and then shift it left 6. Putting the reflection over x in purple. And then left 6. Okay. When you're done, take a look up here, see if you have the graph in red that I have. By the way, I'm going to get rid of the parent graph and the intermediate step. Bottom line is that when I ask you to sketch the graph of negative square root of x plus 6, this red graph is what you should end up with. And charting the domain and the range of this is something that can be done by inspecting the graph. So when you inspect the graph, the red graph, what do you get for the domain? Tommy. Domain appears to be what? You say you're not sure? What you can do is think of the domain as a set of x values that get to participate in the graph. So as you look at all the x values, what's the least of all the x values?
Negative 6.
So your domain's going to be negative square bracket negative 6. What's the greatest? To infinity. So if this were a hot dog question, you would look at the x coordinates of the graph, the participating x coordinates there. How about, Jonathan, what would you write down for the range of this function?
Infinity, well, that's curve bracket, infinity.
Actually, it's negative infinity, because the least, it's going all the way down to negative infinity.
0.
Up to 0. Okay. Now, you now are one short step away from the domain and the range of f inverse. So the next part of this problem would be to list a domain and range of f and f inverse. What would the domain and range of f inverse be? Help me with that, please. Lauren, the domain? Not sure? Nice thing is that to find the domain and the range of the inverse, they're just the domain and the range of the function switched. The domain, it's not just x and y that trade places, it's domain and range that trade places. So what's the domain? Then negative 6 come infinity. So this will help you accurately flip the red graph over the line y equals x. So sketch the graph of y equals x, and let's flip the red graph over this line with our attention focused on the domain and the range, because the graph that we come up with had better have a domain of negative infinity to 0 and a range of negative 6 to infinity. Let's try it. Instead of negative 6 comma 0, plot 0 comma negative 6. And notice that you also have to go through, if the red graph goes through the line y equals x, which it doesn't always, but if it does, then the blue graph will have to also. So it looks like and that looks symmetric when you take red and blue together. Is this blue graph really a graph whose domain is negative infinity to 0 and whose range is negative 6 to infinity? It looks like it. So, this domain and range of f and f inverse, and then sketch f inverse. So if this were a hot dog question, the only thing that you'd have to put on the hot dog bun would be the graphs of f and f inverse and their domains and ranges. So this is what we're shooting for. We need to practice this one more time before we launch into an actual hot dog question. Thomas?
Wait, how do you know the blue graph is like that?
Well,
How can you do that without
without a calculator? Well, first of all, if your original function is a square root graph, then its inverse will be either the right half of a parabola or the left half of a parabola. That's the relationship between square root graphs and their inverses. One is a square root, one is a square, okay? If the original function is either the right half of a parabola, the right half of a parabola, or the left half of a parabola, then its inverse will be either a positive square root or a negative square root. So, but the other reason I know that is because it just has to look symmetric. I mean, doesn't this red graph look like what the blue graph would look like when you reflect the red graph over the line y equals x? I mean, just a minute, do you see the symmetry in the graph?
Yeah.
Does it look attractive to you?
Do they have to cross?
No. No, but if red crosses the line y equals x, then so does the other one. Notice what we had in the solutions? See, when red did not cross, then blue did not cross. What was the story over here? But here, red crossed, and so blue had to cross also. Red was a square root graph, so blue was half of a parabola. Okay? So we're looking at more than just the numbers and letters. Practice this one more time. This isn't easy, that's why we need practice. Where are we? We are right here. Okay, so try another one. Attempt to get the whole thing here. I'm going to give you the graph of a function. The equation is in red. Try to get the graph of its inverse and the domain and the range. So here we go. Y equals negative square root of x plus 9. And that's f of x, by the way. Sketch f and its inverse and chart the domain and the range of each. Try this one on your own, on your collection packet. Reflection over x up 9. Those are the transformations. Reflect over x axis. Shift up 9. It's often during the hot dog game that students learn concepts for the first time. Oh, now I understand. Might be your experience. Okay, see how we're doing on the graph of f. Hopefully you took the parent graph square root of x, reflected over x, and shifted up 9. So the endpoint should be at 0, 9. And I'm going to take the parent out of the picture and the purple graph out of the picture. Raise your hand if this is the red graph that you came up with, or the graph that you came up with for the parent function. Glad you got that. Hey, put the graph of y equals x on there. And see if you can complete the diagram, make sure it includes the beauty of symmetry in the context of y equals x. Is there a volunteer who'd be willing to come on camera, take the stylus, be willing to be publicly named as the person who sketched the graph of F inverse? It'll be in blue. It's already selected in blue. It will not contain the point 0, 9. It'll contain some other point. Is anyone willing to give this a go? Take a lot of courage. If you make a mistake, it's not the end of the world. Who knows? It might even result in this video going viral. Is there a volunteer? If you change your mind at any point in the process, you can let me know. Might be willing to let you come in. Can someone at least tell me the coordinates of the endpoint? It's not 0, 9. What would the coordinates of the endpoint be? So what do you think, Jack?
Yeah, Jack.
For the blue graph, what would be the coordinates of the endpoint? I'll give you a hint. It's not 0, 9. 9, 0. Okay. Now do we have any takers? Now that you see the endpoint and the need for symmetry, maybe you see in your mathematical imagination where F inverse would go. Is there a volunteer who'd be willing to take this stylus? Do you want to give it a go?
No.
You'll remember this for a long time. And if you forget, you can go and watch it again. Jen, you want to give it a go?
Hey.
Thank you, bro.
Gerald, yeah, here we go.
I could be wrong. Uh-oh.
You know what, you almost got it. Tell you what, to get the symmetry, one thing I'll coach you on is that whenever the red graph hits the line y equals x, so will the blue graph. In fact, the blue graph will hit the line y equals x at the same point, so that blue, red, and black will all come together at the same point. Okay, so you were almost there.
Oh.
Yes! That's it. Let's give him a hand. That was Gerald, ladies and gentlemen. All right, so see, notice that red, blue, and black came together at the same point. That's what we were looking for. So if you didn't get that, let's label it F inverse. This one is F. And now, let's list the domain and the range. I'm really happy with you. Okay. So, let's see what you got for domain and range. This is awesome. Got domain, range for both F and F inverse. Here we go. So, write it down. Owen, what'd you get for the domain of F? 9 to infinity is correct. How about the range?
50,
Let's see. As I look at this red graph, think about, of all the y coordinates that participate in the red graph, what's the least of all of them?
the least?
Yeah. This thing actually goes
So
down
negative.
forever. It's not going there quickly, but it's what? I'm sorry?
Negative infinity.
it's negative infinity. Yeah, that's, I should have spotted this one. So your domain is not 9 to infinity. What's the least of all the x coordinates that you see in the red graph? No, there's one lower than 9. Think x coordinates. What's the least of all the x coordinates on this red graph? 0 is correct. So the domain is 0 to infinity. And the range is negative infinity up to a maximum value of what? None. Okay, so, and that's a square bracket.
Wait, so how do you know it's 0?
Well, just inspect it. Say, well, let's see, the x coordinates here, like, 20, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. This is the point 0, 9. And that's the smallest of all the x's. It's the least of all the x's that participate in the red graph. So by inspecting the graph, we get 0 to 9, or 0 to infinity for the domain, negative infinity to 9 for the range. Flip them to get the inverse. So the inverse, if so the domain of this thing should be and I just want to make sure, let's see, something is bothering me about this. So range, or domain is 0 to 9, range, or 0 to infinity, range is negative infinity to 9. When we flip that, we should get a domain of negative infinity to 9 and a range of 0 to infinity. Yeah, that's actually correct. So negative infinity to 9, square bracket. Sure enough, the x coordinates, even though it doesn't look like it's going to make it all the way to negative infinity, it will. And the range is going to be from a minimum of 0 up to a maximum of infinity. So, there it is. It's the whole thing. Any questions on that process? The directions on that, by the way, were to sketch f, f inverse, and then list the domain and the range of each. Okay, well, I'll tell you what. Just for time management purposes, before I actually give you the official hot dog question, we have to go through the new material, make sure we finish the notes. And then we'll wrap up then with the hot dog question. So there are notes for today's lesson.
Mr. Rice?
And question, yes, go ahead.
Restroom before our new
Yeah,
notes.
go ahead. Yeah, that's for sure.
Mr. Rose,
Hello?
can I also use the bathroom?
One male, one female, okay, one of each?
Yes.
Oh, yeah, so you're learning the system.
Hey, those of you who want paper notes are right up here. Grab a copy and let's begin. 8.3C. Yeah.
I go once you're
Yeah. After he gets back, it's only emergencies.
Mr. Rice?
One after another.
I don't have respect for my wrist.
Yeah, you'll just, it's just, I know a lot of people want to leave as soon as the teaching begins, but hang out here. I've had those before. You'll last till the end of class, so just wait till after class. All right, let's begin. We are on the review, and on this quick review, I'd like you to do problems 1, 2, and 3 on your own. These should be quick sketches. So we're doing problems 1, 2, and 3. Sketch the graph of y equals x squared minus 2. And if you just want to get the general shape that it's a parabola that opens up from the point 0, negative 2, that's fine. We're not going to make you get every point accurately. The same parent graph, which I have here in green, y equals x squared, is the parent graph for all 3 of these. So what would the transformations of the parent graph y equals x squared be for this one? What do you think about this one, Mia? The -2 for small performs what transformation?
To the right.
Yeah, that -2 takes us right to. Then how about the +1, Jay? What would the +1? Yeah, that'd be up 1. So go ahead and transform the x squared parent graph right to up 1. And you don't have to do anything more than just draw the general shape of a parabola. And then try number 3 on your own. Hopefully you're doing a reflect over the x-axis followed by up 2. And it's going to end up looking like this. Any questions on the first 3 problems? Reflect over x, shift up 2. All right. Yes, Anna, go ahead.
On the first one, why are there 2 graphs?
Oh, I just put the parent graph on there, y equals x squared, and shifted down 2. Further questions?
So we don't have to add
You have to have the final answer, and that's it. Now, these are misnumbered. This should be problem 5 and 6. So let's take 3 to the x. Let's go to review of that parent graph. It's like a population that starts at 1 million people and triples every year. If you just want to write the general shape like this, I want to remind you that you're not done with this until you put in the labeled asymptote at y equals 0. What's the transformation of the graph in number 4 in order to get the graph in number 5? How would you document that transformation? Go ahead, please, Lauren. So what's that minus in front of the x accomplish? A reflection. And a reflection over which axis? Is that going to be the x-axis or the y-axis? Yeah, if the negative had been out front, it would have been a reflection over the x-axis. But because it's right next to the x, it's a reflection over the y-axis. That's right. I mean, just imagine taking the opposite of every x-coordinate on the blue graph. So reflect the graph in number 4 over the x-axis, you get this general shape. Not complete unless you sketch the asymptote here. Now on the quiz that I graded yesterday and we'll hand back to you today, some of you blew past the asymptote and you did stuff like this. The stuff in blue, you went like this. Woo! It's like, wow. Hello, honor the asymptote. You can't just go cutting through the asymptote like that. The asymptote basically gives you a limit on where the graph can go. When it comes to horizontal asymptotes, these graphs, there are graphs that will intersect horizontal asymptotes, but not these. This is a nice review problem here. There's a lot of transformations. I'm going to put the parent graph on. And I noticed that some of you had trouble on the quiz, apparently because you didn't take the time to sketch the parent graph. So parent graph's got to be there if you're having trouble. So the negative out front, what transformation does that cause us to experience? Let's go with Imani.
The negative out is reflect over x.
Negative out front is reflect over x, that's correct. The -2 up here, I'm going to go to magenta for that. What transformation does that accomplish? Help me out with that one, please. Oh, let's go to Mason. Mason, the -2 here, what transformation does that give us?
Left.
It's, it's actually, it's going to be a right 2. We just use the inverse transfer, the inverse operation. So -2 is going to go right 2. And since a +1 affects y, it would be y -1 on the left, and we would take the inverse of that also. Instead of -1, it's going to be adding 1 to all the y's, so that last one is going to be up 1. So up 1 is correct. Go ahead and perform all 3 of these transformations on the parent graph 4 to the x. So I'm doing reflect over x in purple. right 2 in magenta, and up 1 in red. Why would I not get full credit for this graph that contains the point 2 comma 0? Yeah, I'm missing the asymptote whose equation, I mean, the asymptote has to be drawn, and its equation should be labeled with the equation y equals 1. Any questions on review problem number 6? All right, so this is the kind of thing that was probably like the hardest question on the quiz in terms of graphing. Problems that had a total of 3 transformations were the ones that gave you the most trouble. All right, here we are on page 2. Okay. So, just like in the practice hot dog work we did, we need 3 graphs. F, the line y equals x, and F inverse. Try problems 1 and 2 on your own. Or 1, it's actually B part A and B part B on your own. Okay. So, x squared. I'm gonna make it a little neater. That's, but here's x, goes to the point 2 comma 4. Going for beauty here. So let me make this a little more accurate. Make sure your line y equals x really does have a slope of 1. Go through the appropriate points of intersection, label it y equals x. And when you take each point on the red graph and let the x and y coordinates trade places, should look like this. A parabola that opens up and a parabola that opens to the right. Questions on this? Alana?
How do you know when it's like a parabola versus just a line with the asymptote?
Okay, yes, that's actually, I'm glad you asked that. Now, the line with the asymptotes will be either a log graph or a function that has a variable exponents. So if you see an exponent that is a variable, there'll be an asymptote involved. But look at this exponent. This exponent is not a variable, it's just a constant. So x squared is one of our parent graphs. And so there's not many parent graphs in this course. We ask you to get to know them. If you ever forget what the graph of a parent graph looks like, you could do point plotting. But y equals x squared, we do expect you to say, oh yeah, that x squared parent graph is the shape of a parabola. But you can tell by studying the equation when the x is not the base, but rather the exponent. When the x is the exponent, that's the signal that you have a horizontal asymptote. Okay, like for example, let's skip to part C. Compare part C to part A. In part C, the exponent is x. So that tells you you're going to have an asymptote 1, 2, 3, 4, 5. This is exponential growth when the variable is in the exponent. And so number 5 looks like this for the original, which I've been putting in red. So before we do part B, skip ahead now to part C and do your best to sketch the graph of F inverse by reflecting the red graph over the line y equals x. Give it a go and then label it with F inverse. The graph takes what appears to be a sharp turn. It's actually smooth there, but at 1, 0, it's coming up, takes a sharp turn. Don't forget the vertical asymptote at x equals 0 and enjoy the beauty of symmetry when you combine the graphs of f and f inverse. So, Alana, have I answered your question then about how do you know when there's an asymptote? That's the basic question you had.
Yes.
Yeah, okay. All right, by the way, part B, I did ask you to give part B a go. That should have been a graph with an intercept of -1 and a slope of 2, so you're going up 2 over 1. You're on grid paper here, so with linear functions, you probably remember how to get these to look right. Note that the line y equals x does go through 1, 1, as always. And the inverse of f inverse would have an intercept not of 0, -1, but of -1, 0. And instead of a slope of 2, it's going to have a slope of 1/2. I mean, it's got to go through. Remember when Gerald was up here, red, blue, and black all came together in one point? So we know what point to go with. When you look at where red crosses black, you got up 1 over 2, up, just continue that pattern. So when you did part B, the answer should have looked like this. Red, blue, and black coming together at the point 1, 1. Any questions on parts A, B, or C? Yeah, Gerald.
So for B, like, why is it, probably a stupid question, but it's straight lines, I kinda missed the first part, but
Right, so that first part,
like you going up 2 over 1 instead of doing like a parent function.
well, you know what? That actually is a child of a parent function. It's a parent function we don't talk about much because it's this parent function. And it's actually, that parent function is vertically stretched. It's actually vertically compressed by a factor of 2 and then shifted down 1. Vertically, it's vertically stretched by a factor of 2. It's horizontally compressed by a factor of 2, which is equivalent to a vertical stretch by a factor of 2.
So if it was just x minus 1, it would be on the, it'd go down 1 over 1 from the 0, what is it?
Okay, so if I understand your question correctly, you're asking, what if the original equation had been just x minus 1? Is that it? Okay, so that would be a linear function whose intercept, y-intercept is still -1, but its slope would be +1, up 1 over 1,
Right,
instead of up 2 over 1.
right, okay.
Okay?
That makes sense.
Yeah, so that's, what we're doing here is we're reviewing some of the previous parent graphs and their transformations. Now, today, we're introducing you to a whole new neighborhood of parents. Each one owns a home in the neighborhood. We've got the log base 2 of x parent graph. It's a new parent. Meet the parents. Log base 3 of x is a new parent. We've got log base 4 live in this neighborhood, log base 5 of x, log base 6 of x. Let's look at this new parent graph. It's not y equals x squared. It's not y equals 5 to the x. The log base 2 of x parent graph, get to know it because we're going to be taking this parent graph and shifting it up, down, left, and right, reflecting it over the x-axis. We're even going to reflect it over the y-axis. You ready for this? Here we go. Here's a new parent graph, log base 2 of x. It's really the inverse of the 2 to the x function. It contains point 1, 0, and that's, I know it's 1, 0 because the log base 2 of 1, let's think about this, eyes up here. I know this seems small, but it was like an epiphany to me when I realized that to evaluate log base 2 of 1 or log base 2 of anything, all you have to do is look at the base and the input and ask yourself, what exponent goes on here to get that number? Class, what exponent would you have to put on, wait, eyes up here. Log base 2 of any number can be potentially really confusing for students. Here's all you have to do. Start with 2. What exponent do you have to put on 2 to get 1? 0. 0 is actually 2 to the 0 is equal to 1. That's why the log base 2 of 1 is 0. Golf ball 1 is at a height of 0. How about golf ball 2? So that's equal to 0. If you don't believe it, do the arrow thing. 2 to the 0 equals 1. What's the log base 2 of 2? Or in other words, what exponent do you have to put on 2 to get 2? Class? 1 is correct. So golf ball 2 goes up to 1. Now the next one that would be interesting, where you could do it in your head, would be the log base 2 of 4. 2 to the what power is 4? 2 is correct, so that means golf ball 4 goes up to 2. What's the log base 2 of 8? 2 to what power gives you an 8, class? What exponent do you have to put on 2 to get the number 8? Call it out, I can't hear you. 3 is correct. So if we had room to fit golf ball 8 on this, we'd go up to 3. But here's what the parent graph looks like here. But it also, like 1/2 would be an exponent of -1. So we go down here. That parent graph always has, because of the reflection over the line y equals x, it has a vertical asymptote at x equals 0. So there it is. That's full credit for the graph of log base 2 of x. Log base 3 of x is almost the same. I'll do it in red. But instead of they all go through 1, 0. Because log base anything of 1 is equal to 0. But here we'd have to go to golf ball 3 before it goes up to 1. Log base 3 of 3 is equal to 1. So the log base 3 graph, what do the graphs have in common? They both have an x-intercept at x equals 1. Every member of this neighborhood, all the parent graphs that live in this neighborhood, we'll call it the log neighborhood, where all the houses are made out of aluminum, they all have an x-intercept at x equals 1. And what else do they have in common? They all have a vertical asymptote at, and you know, blue's going to show up a little bit better on the camera there. So they all have a vertical asymptote at x equals 0. Basically, they all have, all the families in this neighborhood have a vertical asymptote. Their parent graphs have a vertical asymptote right there on the y-axis. How are the graphs different? Well, I'll tell you what. Depends on the base. So their 2 points that they have are 1, 0 and b, 1. So where they differ is in the x-coordinate of the second point. You can think of all these parent graphs as having a point at 1, 0, and then whatever the base is, 1. So it's like 2, 1 for log base 2, 3, 1 for log base 3. If it were log base 45 of x, then there would be a point at 45, 1, because the log base 45 of 45 is 1. So, without a calculator, sketch these. Here where b is equal to 7, you're going to plot the points 1, 0 and 7, 1. When b is equal to 10, it's going to be 1, 0 and 10, 1. Here we go. These don't take too long. For 7, the graph's not big enough, so let's go by 2's. 2, 4, 6, 8, 10. So we need the points 1, 0, which is right here, and 7, 1. That's the graph of log base 7 of x, put in the vertical asymptote at x equals 0. Sketch the graph of log base 10 of x on your own. Make sure you include 2 points, 1, 0, and b, 1, where the base b is equal to 10. 2, 4, 6, 8, 10. One, 0, and 10, 1 are the 2 points. Then it's got to make a hard turn. It's not really it's not like a right angle or anything, but put in your asymptote at x equals 0. Any questions on this page? It's the neighborhood populated by homes parented by log graphs. They're all, Gerald, go ahead.
So 1, 0 and b, 1, is that always going to be like our formula when we are?
It's like if you want to get 2 points on a log graph, yeah, that is a formula. All log graphs contain the points 1, 0, and then whatever the base is, 1. I mean, think about it. Suppose the base was 97. What's the log base 97 of 97? Well, what exponent would you have to put on 97 to get 97? It'd be 1. So that's why golf ball 97 would go up to 1. 97 comma 1 would be the point. Let's go to the next page. Okay, so it says sketch these without a calculator. The idea is that we got the log3 parent graph, which, I mean, I'll put the parent graph in green. Actually, you know what, on the homework solutions, I've been putting the parent graph in blue. So the parent graph is log base 3 of x. We just learned how to do that. It's 1 comma 0 and 3 comma 1. And yeah, Gerald, I'm not afraid to say publicly that on the quiz, your graphs were like really good. In fact, you even brought more than one color to the quiz, and you were doing your parent graphs in one color and the final graph in another color. It was a thing to behold. I mean, it's been over 12 hours since I've graded your quiz. I still remember it. I see it. I see all these graphs in my mind, multicolored, really exciting. So we got this parent graph, and which way should I reflect that, by the way? This +1 indicates that I said reflect. Which way are we gonna shift this one? You know, the +1, it means what, class? It means left 1. So vertical asymptotes on log parents are sensitive to only left and right shifts. Do you remember how exponential parent graphs had asymptotes that were sensitive only to up-down shifts? For log graphs, it's only left to right. So let's get the answer up here, and then I'll take Alana's question. We're going left 1. So those 2 points get shifted left 1. Here's our final answer. Alana, go ahead.
Can you just like zoom on each graph that
Yeah.
you're working on?
Let's do a graph, called the graph zoom operation, which is actually not the easiest thing to do. It's going to take a lot out of me. Oh, there it is. So notice we took the blue graph containing the points 1 comma 0 and b comma 1, or 3 comma 1 in this case. Both those points went 1 unit left. Even the vertical asymptote went 1 unit left.
Which color is the one that's?
I'm going to be doing, in this lesson and on the homework solutions, I'll be doing parent in blue and final answer in red. So final answer, I'm always putting in red, start to finish throughout the entire unit. Actually, the whole school year I've been doing that. Final answer in red, or boxed in red. Okay, so try part B on your own. Give part B a go. Try sketching both the parent graph and the child graph. Kind of makes me wonder what would happen if I were to zoom in and then draw on it? I'd have to be able to get the color palette into the zooming window. I have no idea what's going to happen when I try this. So far, so good. It's not going to overpower the system, is it? It smells smoke or anything, do you? Okay. You do.
If it's that much of an issue.
No, it's actually not. Nothing's burning up. Nothing's exploding. It's zoomed in. I kind of like this. So the parent graph in blue is 1 comma 0, 2 comma 1. And I'm looking at, oh, see that? See, it did. See, I'm drawing here. Oh, well, no, it recovered, I think. So this -2 is going to be a right 2, so I'll do that in purple. Huh. Yeah, there's an extra procedure I need to go through to make it work, but it looks like it's working. That's right 2, and then up 3, we'll go final answer in red, so 1, 1, 2, 3. And another thing you might notice about my solution sheets, this is actually really interesting to learn the nuances of this software. I've always been putting the main point that we're tracing in yellow. So this was the point 1 comma 0, but we shifted it right 2 and up 3 to the point 3 comma 3. So the final answer is to ignore everything except for the red curve and the green vertical asymptote, which needs to be labeled as x equals 2. guess there's only so far. There we go. Just any questions on part B? All right, I think we're okay. Now, I think you know enough now that you'll be able to do part C and D. Give part C and D a go. Get the parent graph and the child. Please document your transformation. I'm going to tour the room to see what documentation you generate for parts C and D.
All right.
Here I come. Document your transformation. Alrighty. Well, what transformation did you document on letter C? By the way, the parent graph's going through 1, 0, 5, 1. 2, 3, 4, 5, 1. So parent graph looks like this. So documentation, help me out with that, please. Let's go with Jonathan. What documentation would you generate for the reflection in part C? I mean the transformation in part C. It is a reflection. Which reflection is it? Okay. Well, since the negative is not right in there by the x, it's not influencing the x, it's influencing the y. That negative sign is actually changing all the y's from changing positives to negatives and negatives to positives. So if you, think about this. This is the point 1, 5. If you change the y coordinate to this point to -5, I'm sorry, it's not 1, 5, it's 5, 1. So if you change the y coordinate by multiplying it by -1, what would it do? Would it reflect this point? Again, this is the point 5, 1. If you change its y coordinate by a factor of -1, make it 5, -1 instead, would that reflect the point over the x-axis or the y-axis? It would reflect it over x. So when negative is by y, it reflects over x. When the negative is by the x, it reflects over y. Okay? It's just that backwards movie idea that's like it's not what you would expect when you see. I know you came, you said with a +2, you said, oh, it's going to be down, but okay. So, reflect over x. All right. So, final answer is not just this guy right there in red, but it's also the vertical asymptote x = 0. And hopefully what you did see there, Jonathan, there the negatives by the x. So what's the documentation going to be this time?
It's going to be.
Yeah, when the negative is by the x, we reflect over the y-axis. And this was a weakness on the quiz, but you know what? Better late than never. You have a chance to redeem yourself. It's not too late to learn. So reflect that over the y-axis, and it goes like this. No full credit unless you label the vertical asymptote at x = 0. And now on the bottom here, the last example of this lesson is taking log parent graphs and doing 2 transformations on them. Take the parent graph log 7 of x, which, you know what, the basic shape of it, let's just go back to 1 point. The basic shape of it is, it goes through 7, 1, but it looks like that. So, let's make sure you have this. And remind me, what does the negative sign way over here do? Let's go to Daniel. What transformation is signaled by the negative sign located here?
U like reflects over X.
Yes, it's a reflection over X, good job. And then the -1 is gonna be the old right one. So class, try it, try both transformations. Take the parent graph, reflect over X, go up 1, see what you come up with. Zooming,
Well, you said right one and you went up one.
Yeah, why isn't it?
yeah, what's up with that? What, get it, what's up with that? Because it should be right one. So look at this, we'll change it, instead of, I was too excited about zooming. But, you're right, I went up 1, but I should have gone right 1. So, wow. Once it gets to the point where you're correcting my mistakes, and that shows a lot of good understanding, so it should be right 1 with a point at 2, 0. The vertical asymptote was also influenced, so that green vertical asymptote should be at x equals 1. And because there's a fair bit in this graph that could make it appear cluttered, we're gonna have to zoom in. This thing has some effects. 2, 0 is the point. 2, 0, vertical asymptote x equals 1. Any questions on part E? Okay, so for the sake of complete notes, let's get this last one. This is, negative sign here is by the x, so we reflect over y. And then we're gonna try to go down to, try it on your own, then check your answer with mine. It's a log base 3 parent graph. Reflect over y. Go down to. And it looks like the vertical asymptote stays put because there were no left-right shifts. The special yellow point is at -1, -2. It went to -1 on the reflection over y, it went down 2 on this transformation. Any questions on that one? Just so you know, the homework that's due Friday is this worksheet, paper submission. Guess what? The solutions are already on Academy Central, which you can view using your phone. You want? No, not yet. And then there's just a quick FYI. Friday's lesson, as advertised, is being taught today. It's just one sheet of paper. Log properties, I don't know if you realize it, but the log properties are just raise, multiply, add, and divide, subtract, repackaged for Algebra 2. So if you understand raise, multiply, add leaves not part of the deal, but and divide, subtract, then you'll get the log properties. So, get ready, it's Friday's lesson. I'm teaching Friday's lesson today. All right, here's the homework. Homework's a worksheet. Do the worksheet for Friday. All right, here's the log properties. Class, check this out. Review. When you see the word log, what the question?
Do we have 2 homeworks due before tomorrow?
Sadly, there's only one homework due tomorrow. The other homework, like the lesson I'm teaching right now, this is Friday's lesson. You'll be able to do it in class. It's not due till after spring break.
Yay.
Okay?
So the 3 point,
Question? Yes.
We didn't get the homework.
No.
So wait, only the
Homework
worksheet?
sheet.
Is there a homework?
The only homework due Friday is that worksheet that I just handed out.
the 8.3.
Oh, you didn't get the homework. Thank you for telling me. Appreciate that. All right, here we go. This ought to be interesting. There it is. Now, friends, what is a logarithm? In one word, if you had just one word to describe a logarithm, what would that one word be? It's an exponent. There you go, Owen. It's an exponent. So think of this as multiplying. M and N are both exponential expressions. When you multiply exponential expressions, you add the exponents. A log is an exponent. So if you want to know what is the exponent of a product, just think multiply, add. When you multiply exponential expressions, you add the exponents. Divide, subtract. When you divide exponential expressions, you subtract the exponents. And when you raise exponential expressions to a power, this is raise multiply right here. So this is raise multiply down here in log form. This is multiply add. This is divide subtract. So today's lesson is really stuff that you learned in pre-algebra, but it's expressed in log form. So let's practice doing this. By the way, these equations operate in two directions. They're two-way equations. If you're given this half, you have to go and move to the right. Sometimes you'll be given the right half and you're going to have to move and replace it with the left. Like for example, here, we have a sum of logs. Well, a sum of logs is the same thing as the log of a product. This is how I store these equations in my imagination. I go LOP for log of a product, and this is SOL, the sum of logs. A log of a product is the sum of the logs. That's the phrase that's probably going to help you remember this the best. So when I say go, would you please say out loud and in unison, the log of a product is the sum of the logs. Try that. Ready? Go. The log of a product is the sum of the logs. Okay, try it again. This time, let them hear you in cyberspace. Camera has a microphone. Let them hear you. When I say go, I want you to full voice project. The log of a product is the sum of the logs. Ready? Take a deep breath. Go. The log of a product is the sum of the sum of the logs. Much better. So when you see the sum of the logs, just write that as the log of the product. Log base 2 of 24. It's pretty good. Now this is a difference of logs. Tell you what. The log of a quotient is DOL, the difference of the logs. So when you have the difference of two logs, that's just the log of the quotient, 16 divided by 2, log base 3 of 8. It's log base 3 of 8. Now, the third property is that when you have an x out front like this, that can go up and become an exponent. So this 2 out front, this is really raised multiply in disguise. Just rewrite that as 3 squared plus log base 5 of 2. So that 2 comes up and sits on the 3 as if it's 3 is wearing a hat, and 2 is 3's hat. Simplify that to the log base 5 of 9, and since the sum of logs is the log of a product, what is the log base 5 of 9 plus the log base 5 of 2? Who can give me the answer on this one? What's the sum of the logs in this case? Andrew, do you want to give that a go?
Log 5.
It's the log of the product, and so multiply them.
18.
You have to log base 5 of 18 because the sum of logs is the log of the product. Multiply them together. So this one has 3 of them put together. The first step is to put the numbers out front back up in the exponent position. So it's log of x to the 4th minus log of y plus the log of y squared. That's the first step, to put the hats back on the heads. Second step is to take difference of logs, rewrite that as the log of the quotient x to the 4th divided by y. But since it's a plus sign, it's going to be multiplied by y squared. So divide when you see subtraction, multiply when you see addition. When you simplify that, the final answer is log of x to the 4th y. Just because y squared over y simplifies, y squared over y just becomes y. So that's the final answer right here. So that's condensing, taking an expression that has many logs and condensing it to an expression that has only one log. We expect it to go the other way, take an expression that has only one log and expand it out. So it's going to be the log base 7 of 4 plus the log base 7 of x plus the log base 7 of y cubed. But the 3 comes down front to become 3 log base 7 of y. Here we have the log of a quotient, which is the difference of the logs. So because you're dividing, using divide subtract, the exponents go log base 8 of 15 minus log base 8 of y. I love part C because it requires you to remember log of 6 plus the log of the square root of 3x. But it requires you to remember that the square root symbol is an exponent of 1/2. You might be wondering, what did you just write there? Okay, yeah, that was a little bit messy. The log of a product is the sum of the logs. Log of 6 plus the log of the square root of 3x. But can't the square root of 3x be written as 3x to the 1/2 power? So I can simplify this further, making this log of 6. The 1/2 using raise and multiply means I need to multiply the exponents. And log of 3x is the log of a product. So it's log of 3 plus log of x. You'd have to distribute that through to get the final answer. This 4 comes down front, so it's 4 log base 2 of 3x. But 3x is a product, so it's log base 2 of 3. The log of a product is the sum of the logs, log base 2 of x. To get the final answer, you'd have to distribute through the 4. Now, I want to make sure you get these examples on the last page, which actually are kind of fun because they simplify all the way down. In these last 4, let me just talk you through this. Since the sum of 2 logs is the log of a product, we got log base 4 of 16. But this one can go further, because what is the exponent that you put on 4 to get 16?
4.
4 to the second is that. So, yeah, these go pretty fast because since it's subtraction, we divide. 50 divided by 2 is 25, and the exponent is 2. On this one, we put the 2 back up top, so it's log base 4 of 36 minus the log base 4 of 9. But 6 squared is 36, so it's going to be 36. 36 divided by 9 is 4, and oh, that should be 4. And the log base 4 of 4 is 1. So, we'll work on the homework on Friday. You are dismissed.
Are you going to the AP World Fair?
Oh, that's, yeah, I'll go.